his advisor, and I think he's halfway through writing his thesis. In fact, he will defend soon. Next year he'll be here again at Caltech as a postdoc between LIGO and CaJAGWR, and he'll tell us about compact binary coalescence searches.
Thank you. So I'm giving this talk on behalf of the LIGO scientific collaboration and the Virgo collaboration, and it is about progress in the LSC Virgo search pipelines for compact binary coalescences. Just as an overview, this talk will focus mainly on the search for low-mass compact binary coalescences in LIGO's first calendar year of its 5th science run. And that will include a summary of the pipeline that we used for the search, focusing on new developments and also results from the search. At the end, I'll also spend a few minutes talking about additional S5 searches that we're performing, which are the low-mass compact binary searches in LIGO's 2nd year of its 5th science run, and a joint search with Virgo's VSR1 data, and also the high-mass compact binary coalescence search. So to start off, I'd like to acknowledge a few people, especially my wife and our little dog. And then also I'd like to thank my advisor, Alan, for all the help he's given me with this. I'd like to thank the Compact Binary Coalescence Group as a whole, because they've been very important in producing this result, and also the LIGO scientific collaboration and the Virgo collaboration. Then also I'd like to thank many individuals that have passed through the halls of Milliken's 6th floor for all of their help and conversations that they've had with me. So focusing on the search for low-mass compact binary coalescences in the first calendar year of LIGO's S5 data, we're searching for coalescing binaries, which are 2 compact objects, either neutron stars or black holes, that initially are orbiting each other in an inspiral, that then coalesce in a merger and ring down. And these form the 3 different phases of the waveform that we can search for. In this search, we're looking just for the inspiral phase, because that's what, when the search was started, that was all that we had templates for, although now numerical relativity is really filling in this question mark that Kip drew so many years ago. For the S3 and S4 searches, we had 2 separate searches that were focusing on different parts of the mass space. We had a low mass search, which was post-Newtonian templates using the stationary phase approximation. So these templates were physical templates in a sense. And we also had the high mass search focusing on this larger region, which used BCV templates, which are phenomenological templates, and they didn't correspond to physical parameters in a way that we could use to our advantage as much. For S5, we've extended these mass regions to be going to higher total mass, extended it up to 35 solar masses in total mass for the low mass search, and up to 100 solar masses in total in solar mass for the high mass search. The low mass search is again using the SPA templates, and instead of using the BCV templates for the high mass search, we've replaced those with the effective one body IMR templates, which are commonly known as EOBNR templates. Here's an example template bank for the low mass search that we've performed in the S5 first year. You can see that it starts at 1 solar mass for a single component object and goes up to 34 solar masses for a single object, and also goes up to 35 solar masses in total mass. When we're actually analyzing the data from this and looking at the different regions of parameter space, we break this up into multiple regions, including the binary neutron star region, or BNS region, which is this low mass corner, which made up basically all of the previous template bank that we used for this search. We also have a canonical binary black hole region, which is centered around 5 solar masses in each component mass. And then we have this black hole neutron star region, where we have one object that's a neutron star and the other object is a black hole. finally, in the end, we also break things up in total mass to set upper limits on rates or to get detection on rates for specific solar mass objects as a function of the total mass. To give you a sense of how sensitive the previous searches were compared to this search, this is a plot of the Inspiral horizon distance from S3, where actually you can't see this right here. This says Inspiral horizon distance in megaparsecs. So this is defined as the distance to an optimally oriented and optimally located binary neutron star with solar masses 1.4, 1.4 in each component mass, who would be seen, or which would be seen at an SNR of 8. So for Hanford H1, we see the red. Over the course of this run, the horizon distance was around 5 to 10 megaparsecs. For H2, also located at Hanford, which is the shorter interferometer we have at that site, we have roughly something half that of H1, and then Livingston was in green. This improved for S4 by a little over a factor of 2. And then S5, again, a factor of 2 increase. And our most sensitive detectors were sensitive out to 30 to 35 megaparsecs for the Inspiral horizon distance. So that was just for binary neutron stars. This horizon distance is very sensitive to the mass of the objects that we're searching for. So here I've plotted the horizon distance as a function of total mass. And this is the point where binary neutron stars were. If we look at how sensitive these detectors are to objects at higher total masses, we see that between 25 and 30 solar masses, which this search covers, we're sensitive out to 150 megaparsecs. So now I'd like to give a brief overview of the search pipeline we employ. This is a hierarchical pipeline. So we start with the data, do some stuff to it, do some more stuff, repeat steps, and then in the end we have our final triggers. First of all, we take data from each of the detectors, and then we produce a template bank for each of the sites. This template bank, as I said before, covers the component masses from 1 to 34 solar masses, with a maximum total mass of 35 solar masses. Once we have those templates, we then match filter the templates with the data. Again, these templates are stationary phase approximation templates. And we then take all of the triggers resulting from that match filtering and do a coincidence between them, where the coincidence test that we're applying is now utilizes the metric which we produce the template bank with. And it is a metric on the parameter difference space. We also ensure that a trigger is present in at least 2 detectors in order to pass this stage. And we estimate the background during each of the coincidence stages, this one and this one, by performing time slides where we shift the data between multiple detectors with respect to each other, such that there's a non-physical time shift between 2 triggers from multiple LIGO sites. At different stages of the pipeline, we also employ signal-based vetoes and instrumental vetoes, which help to reduce the background triggers and give us quieter data to work with. Again, this is an example of the template bank that I showed earlier. And you can see that there's little stripes in this, which lie, or the density of this shows you where the template bank, the waveform is changing most quickly. So in this high mass region, the metric that we use to create this template bank is not changing very much. So we don't need very many templates to capture all of the signals in this region. However, for the low mass region, the metric is changing very quickly. So we need many more triggers, or many more templates down there, and a higher density of templates.
How many templates are there?
In total, for this bank, there's roughly 6,000 templates. Yes?
So in numerical simulation of a binary does not depend on the mass m, but the scale invariant. So these must all be detector characteristics, is that true?
That's right. We create the template bank using the power spectral density of the detector, which weights how important different portions of the waveform are. So the mesh filter is made up of these many complicated equations, and it results in a signal-to-noise ratio that we can threshold on. And Chad has made a nice video showing how how we actually perform the mesh filter. Here you see our template that we then will be moving along the data, searching for a signal within that data. So as this moves along, you see that there's mostly noise here. But then at one portion, there's this peak in the SNR, the signal-to-noise ratio, which means that this template is matching something buried in that noise very well at that point. We use a threshold on this and record triggers whenever the threshold is surpassed. And for this search, the threshold was 5.5 for each of the detectors. As I said before, we also utilize signal-based vetoes to eliminate many spurious triggers, which are produced either by glitches or just noise in the detectors. One of those is the CaJAGWR test, which is a test of how consistent a particular piece of data is to a template. So if we have a single template ring up at a certain time above a certain SNR, the CaJAGWR test is performed, and it tells us basically how consistent it is with the data, or how consistent the template is with the data that rang it up. Another signal-based veto we use is an R-squared veto, which looks at the chi-squared time series, and also gives us a different measure of how much a particular trigger looks like the template that it rang off, versus possibly a glitch. Here I show the chi-squared time series as a function of time for a glitch in the data, which has these many pieces of the time series that are above a particular threshold. We look at the number of data samples that are above a particular threshold, and then plot that as the R-squared veto duration. And we can plot that versus SNR for our background triggers, which are time slide triggers, I've shown in blue here, and also for injection triggers, which simulate real signals in the data. You can see that this particular signal-based veto separates the time slide triggers from the injection triggers fairly well. A final signal-based veto we use is the H2, H1 amplitude consistency, or also the H1, H2 effective distance cut. So these we're able to perform because our two Hanford detectors are located at the same site, and thus for a real signal they should see the same effective distance for a particular trigger. The cut is actually shown by these two diagonal blue lines. Anything that is between the lines we keep, and anything outside the lines we throw out. So in red I've shown injections again, and in black are the time slide triggers. And you can see that this throws out many of the H1, H2 triggers that occur in our background. A similar amplitude consistency test can be done when we have a trigger from one detector but not from another. So in that case, we're able to invert this equation and put a threshold on the maximum SNR a trigger can have in one of the detectors if the other detector didn't see it. So after all this is done, we have a set of triggers that have survived coincidence and all of our many signal-based vetoes. And we want to rank these triggers as a function of how important they are, or how loud they are. So we have this big post-processing pipeline where we take in the zero lag triggers and we take in our background triggers, some things, and then rank them again according to the false alarm rate triggers, which we get from the time slide background triggers. For previous searches, we used effective SNR as our detection statistic, which is this complicated equation. It takes in the SNR and chi-squared time series that I talked about before, and it weights the triggers based on both their SNR and chi-squared. So when a template, or when a trigger does not match the template that it rang off very well, it has a high chi-squared value, which suppresses its SNR. So its effective SNR is lower than it would have been otherwise. So this is computed on an individual interferometer basis. And once we have multiple effective SNRs from different detectors that are part of a single coincidence, we combine them by doing the sum of the squares. And that's the combined effective SNR, which we used for previous searches. However, for this search, because we're spanning a much larger parameter space that has vastly different false alarm rates for the different portions of the parameter space, we needed something that was different. Here we're using the inverse false alarm rate as a detection statistic instead of the effective SNR. So first, we divide the search up into regions of similar false alarm rate. And then for a particular trigger, we take its effective SNR, count the number of background triggers or time slide triggers that have an effective SNR greater than or equal to that, and read off that number. We then divide or multiply the background number by the analyzed time for the zero lag triggers, or the real coincident triggers that we have, and divide that by the total amount of time that we searched for background triggers. This is then a false alarm rate that is per analysis time rather than like per second. Because we're doing this for multiple categories in the different regions of parameter space, we also need to multiply this by essentially a factor that is the number of trials that we've done in order to get a real false alarm rate for the combined search. So to give more motivation for why this needs to be done, here I plot the background triggers, the time slide triggers from the full year in all the different analysis times that we have. On the y-axis, I show the effective SNR from the L detector, or the Livingston detector, and on the x-axis, I show the effective SNR from the Hanford detectors. So in the case of a triple coincident trigger, where we had an H1, H2, and L1 trigger, this is the combined effective SNR for the Hanford set. And in the case of H2L1 or H1L1 doubles, this is just the single detector effective SNR. So this we break up into the different observation times that we have, such as the triple coincident time, the H1L1 double coincident time, and the H2L1 double coincident time. Focusing on the triple coincident time, we see that different types of triggers in this triple coincident time have very different background distributions. On the far left, we have triple coincident triggers. In the middle, we have H1L1 triggers, and on the right, we have H2L1 triggers. We see that this set of triggers has a much quieter or much smaller distribution of background triggers than the other two. And this is due to the effect of an additional coincidence requirement. So that suppresses many of the background triggers that would otherwise be there. Another effect that we can see is between H2L1 triggers in two different types of time. This is H2L1 triggers in triple coincident time and H2L1 triggers in double coincident time. We see that the background distributions here have different shapes, and this is mainly due to the signal-based veto that we're allowed to perform in triple coincident time when H1 is also running, although didn't contribute a trigger for these coincidences. Let's again focus on one of those smaller regions or smaller subsets of triggers. These are the H1L1 triggers in triple coincident time. And these again can be broken up into multiple types of triggers. We have H1L1 triggers from the low mass region of the template bank, the middle mass region of the template bank, and the high mass region of the template bank. And you can see that all of these triggers have different distributions as well. The reason we've chosen to break up triggers in this way is because the high mass templates have much shorter durations than the low mass templates. This is because they have a lower ending frequency, so they're not able to accumulate as many cycles, are just shorter in general. This means that when we're doing our match filtering with these templates, they tend to ring off glitches and just other noise in the detector more. So they have a higher background rate than the longer templates that we use from the lower mass region. In the end, we're able to compare different detection statistics using something called an ROC curve. And it tells us basically how we can maximize our efficiency to signals using different detection statistics at a given false alarm rate. So on the y-axis, we have a d cubed weighted efficiency. By d cubed, I mean the distance cubed. For real signals, we expect that they should be uniformly distributed in space. So they should have a distribution that goes as the distance cubed. Whereas the injections that we're actually performing are in log distance. So we have to reweight these injections to make them d-cube weighted. And then on the x-axis, we have the false alarm probability. This dashed line shows what you would get just from random triggers being coincident with injections. And this vertical line shows what your expected false alarm probability is for the search. As you can see, for the low mass region and the middle mass region, using the IFAR as the detection statistic, which is in red, you get a fairly large improvement over the effective SNR as the detection statistic, which is already a lot better than just the standard SNR. For the high mass region, this isn't quite as apparent because this is the limiting region where we're getting the loudest triggers from anyways. So you'd expect the IFAR to behave roughly the same as you'd expect from the effective SNR. So in the end, we have these background triggers, and once the search is tuned and everything, we want to open the box and see what was actually in the data, if we had any detection candidates. And when we did that, we had something that was out here, roughly 10 orders of magnitude above the background. Unfortunately, this was a hardware injection that we left in. We self-blinded. And this wasn't a real detection. We left in 2 hardware injections that were self-blind. One of them we found above the background was found as a triple coincident trigger. And as I said, 10 orders of magnitude above the rest of the triggers. However, the second blind injection was too quiet to be detected above the background and was actually quieter than 10,000 other zero lag triggers, or blue triggers you see here. In the end, these are all of the triggers that came out of the search. We have triple coincident time, H1L1 double coincident time, and H2L1 double coincident time. And as you can see, there were no gravitational wave candidates. Everything was consistent with the expected background, which is given by the dashed line here. Oh, I forgot to say, these plots are the IFAR detection statistic on the x-axis and the cumulative number of triggers on the y-axis. So this shows you the number of triggers you'd expect from background at a particular detection statistic value and the number of triggers that were actually found above that value there.
What are the gray lines?
The gray lines are individual background trials. So in order to perform our time slides, we don't do them just once. We do them 100 different times. And each of those 100 times is then plotted here to show you what the 100 different background trials would look like if it had been the zero lag.
So you would have to have a signal way outside the gray band.
That's right. Yeah. So because we didn't find anything in this search, we want to set an upper limit on the rate that these types of events happen. We have this complicated algorithm for going through and calculating exactly what the 90% confidence level upper limit is. This includes calculating the background probability, calculating the efficiency of the search compared to the software injections that we made, looking at the physical luminosity in the universe to get a sense of the luminosity that we were sensitive to, calculating all the different errors that go into this, and using the loudest event formalism to calculate the rate posterior. So this we do for all the different observation times, and we also combine this with data from our previous science runs, S3 and S4. So on this plot we have a non-normalized probability, just so we can compare the different distributions, versus the rate, which is in units of per year per L10. So we see S3 was not very confining of the rate compared to S4. S5, H2L1, and H1L1 were roughly as sensitive as S4 if you combine the distance that we were able to see with the amount of time that we had for those types of observation times. And S5, triple coincident time, was our most sensitive type of observation time. We can combine all of these curves basically by multiplying them together as likelihoods and get a final posterior on the rate, which we derive our final 90% confidence level upper limit from. And including the data from S3 and S4 improves the upper limit that we're able to set in S5 by 5%. In the end, we have upper limits for multiple types of signals: binary neutron stars, neutron star black holes, and binary black holes. The luminosity of the universe that we're able to see for each of these is 250 L10s, where the Milky Way equivalent galaxy has roughly 1.7 L10s. For neutron star black holes, this is 700 L10s, and for binary black holes, it's roughly 5,500 L10s. The upper limits we're able to set are then roughly 4 times 10 to the minus 2, 2 times 10 to the minus 2, and 2 times 10 to the minus 3. So these are 2 orders of magnitude better than the S3 and S4 searches. However, we're still 2 orders of magnitude away from the astrophysical population synthesis models. So all of these numbers have been calculated assuming that the signals were non-spinning. Something that we've done in this search is also injected spinning signals, where each of the component objects is allowed to have non-zero angular momentum. These change the waveforms slightly with spin-orbit and spin-spin couplings. And in the end, we're still sensitive to these signals, but with slightly less sensitivity.
What kind of spin distributions did you use?
We didn't know the physical distributions because those are still unknown, so we used a uniform spin distribution for both objects.
Uniform on the
uniform,
sphere?
Yes, uniform on the sphere, and also uniform between 0 and 1 in the absolute spin magnitude. Any other questions? We also produce upper limits as a function of total mass and as a function of black hole mass for neutron star black hole binaries. And you can see that as we go to higher and higher masses, first the upper limits get more stringent, and then here we see they're starting to tail off a little bit. And that's the end of the first year search. Next, I'd like to present a little bit of information about the second year search and Virgo's VSR1 search. So something that was also true of the previous search was that we're sensitive to a volume of space that's limited by the antenna patterns of 2 different detectors. For the previous search, this was limited by the H antenna pattern and the L antenna pattern, or the Hanford and Livingston. These two LIGO detectors are mostly aligned, but slightly misaligned. And in order to make these plots, which show the sensitivity in units of distance as a function of sky location, we require, well, for these plots, we just look at each detector's antenna pattern and calculate the distance at which we'd be able to see for each point in the sky. When we combine these, because we look for two detector coincidences, you have to take the minimum of the two. So you end up getting these dual nodes next to each other for Hanford and Livingston. And this really limits our sensitivity for particular portions of the sky. When we include Virgo, we're able to add in a third non-aligned detector, and this improves the reach for many locations above the Earth. And here I've shown the amount of volume that we're sensitive to for Hanford and Livingston, and for Hanford, Livingston, and Virgo. This is roughly a 25% improvement in volume.
What Virgo noise?
This is assuming the Virgo design noise curve, and also the LIGO design noise curves. Something else that you're able to do when you have a third detector is produce sky maps for individual triggers. Because we have three non-aligned detectors, we're able to work out, we have enough information to calculate a sky location, or here a probability for every sky location based on the information from those detectors. This example shows an Inspiral software injection into Hanford, Livingston, and Virgo data. And the color bar is the log of the probability, while the y-axis shows declination, and the x-axis shows right ascension. The red circle you can kind of see right here is the actual location of the injection, whereas the peak of the probability is slightly next to it. Not very far from it, but within the red circle still. Remember, this is log probability, so when you look at this in terms of linear probability, the peak probability is very well contained as opposed to this more colorful map. So now I'd like to present a little bit of information about the high mass search that we're also performing in LIGO's S5 data. As I said before, the high mass search is going from 25 solar masses up to 100 solar masses and is using EOB and R templates. These templates are Inspiral, merger, and ring down, and they capture all three phases of the waveform as opposed to just the Inspiral search that we've searched before. So these templates are no longer limited by the ISCO frequency. We're able to go up to the higher frequencies and obtain more information for each signal. And also these templates were tuned against numerical relativity to match those signals very well. When we use these templates, we're able to search even further horizon distances. So before I showed the horizon distance for post-Newtonian templates out to solar masses roughly, I think 100 solar masses before as well. But here, when we use EOB and R templates, we're able to see even further. So as before, when we could see up to 150 megaparsecs for post-Newtonian templates, when we capture more information and go to higher masses with the EOB and R templates, we're able to see over 700 megaparsecs in horizon distance.
Does this include the higher harmonics in the numerical relativity waveforms?
I don't think so. These,
It's just the LED.
yes, yes. Although they were tuned against numerical relativity waveforms.
Yeah, but most numerical relativity is just cold and now they can do
Yeah.
anything that's what's used.
Yeah, and the waveform that was used to produce this curve is given in a Jeith's paper and a Jeith et al.
Is this for the S5 sensitivity?
This is for the LIGO design sensitivity. So S5 sensitivity.
So this is just from SNR, but is there the high mass part of it? Does it make it to chi-square and coincidence? I mean, there are issues like that.
That's something that we're still evaluating. So. Oh, this is just for raw SNR, but for real injections, we also need to take into account the chi-squared and the other things that limit our search.
So what about the higher harmonics? Do they interfere with the chi-square?
I haven't read anything about that, so I don't know if they interfere with the chi-squared.
You know that the high mass search we're doing where our templates are EOVNR, but we're only injecting EOVNR. And we know that it's dangerous, and so we're loosening up on our reliance on chi-squared. It's still very useful, but we don't loosen up on it.
And that's the end of my presentation. Are there any questions?